in the name of the Almighty, the Compassionate, the Merciful. Last time we talked about real numbers. Now we speak about functions. And our functions are defined over the set of real numbers. And that's what the reason why you started with real numbers. And we said that if you remember that you have two sets and you have a relation which relates the elements of these two sets, such that for every x which belongs to the first set, there is one unique element in the other set. And to every x in A, there corresponds another unique value in y in B, in the other sets. In fact, Euler, in the late 18th century, was the first one to define functions. Prior to Euler, Newton, and Leibniz, they considered functions to be operators working on variables, and these variables, in fact, are associated with graphs and with curves. But now Euler tried to give a more rigorous definition, a definition which covers all these, not only real functions of real variables, but a definition which can also comprise complex functions. And the definition of Euler, he said that a function is a correspondence rule, some kind of relation, which gathers the elements of two sets, such that one can assign a unique value y in the second set called dependent variable, based on a variable, an independent variable x that is chosen freely. And in fact, that was the first definition of a set, of a function. Usually students, when they see x, they reckon it's a real variable. And when they meet z, they say it's complex. This is not true. In fact, both may be either real or complex. That all depends on the codomain of the function. If you are allowing real functions only, then our variables, then all the values of f, all the values of, meaning the value of y, have to be real. And at the same time, we are only allowing real variables x or z. It's immaterial. The only thing that in our study here, we are concerned with real functions with a real variable. In this lesson, we are going to discuss the following. First, we are going to speak about concept of a function. Then, the function as a machine. Later, how to calculate the domain and range of a function. Usually students, they found difficulty in calculating range, but domain for them is easy. And then we speak about the algebraic laws of functions. These are, in fact, the subjects we are going to speak about. First, the function f. Usually, in the old eras, I mean, in the 19th century, usually a function is a relation of this sort. Y is equal to x cubed, for example, minus 3x plus 1, where one can determine y, a unique y, real, given x is real, and all you have to do is that you substitute on the right-hand side for the value of x to calculate the value of y. But as time unfolds, and you have so many varieties of functions, there appears some odd situations in which we encounter the following. For example, in the first case above, to the right here, you have y is equal 1 over x. Now 1 over x here, you can, if you use the calculator, for example, you can assign any value x and then calculate the reciprocal 1 over x, except when you put x equals 0 to 0, you find the calculator gives you a sign of error, meaning that 0, here you cannot replace x by 0 for y is equal to 1 over x. Again, when you have another one to the one which is on the lower side here to the left, when you have y is equal to square root of 1 plus x. Now again here, you may of course allow x to be equal to negative 3. There is no problem about that. And then you get a square root of minus 2. But the problem is, are you allowing y to be complex? If you are not allowing y to be complex, y to be real, then in which case the codomain represent R, for example, then in which case you have to give values or assign values to x starting from minus 1 onwards. In other words, x has to be greater or equal to minus 1. And that's the idea. The idea, these are functions that one finds that they have some difficulty in representing these functions. Again, when you have also modulus x, for example, as a function or the absolute value of x, it's a function which is having a value for x positive and value for x negative, another value for x negative. And this is why mathematicians have tried to put a certain definition for the function which can account for all these problems or for all these variety of situations. So in fact, what is a function? Now, a function is a correspondence rule which assign to every value x in a partial or in a subset of a bigger set A, a value we call a value y, which exists in a larger set B. Now, the value x here lies in what we call the domain of the function. So actually, now x can take any value within the domain of the function. We call it domain, and then render this into the image set R of f, which we call R or range of f. And this actually range assigns to all values of x some values of y here, which belongs to a larger set B. Of course, B here, we haven't spoken about A and B. What are these sets? But we can take them as R, for example, if you are considering real functions. But the most important thing is that you have a domain here, and then you have the rule f, which assigns to every x in D another value y in B, and you have the codomain B, which tells you what values of x in fact you are allowed to use. So in fact, what you have here, you have some characteristic or ingredients of a function. A function, as we said, a rule, and this rule we represented by f of x, like saying, for example, y is equal to square root of x. This is the rule of the function, f of x. And then again, you have the domain of the function. In other words, all the set in which every value x you can use. And apart from these values, which belongs to the domain of f, you cannot use. You are not permitted to use them because the function only accepts those values of x which belong to d of f. And finally, you have the codomain of the function. And the codomain of the function tells you what sort of function you have. Because if you allow the codomain to be restricted, then you might restrict as well the value of x which you can use. If you take it as C, the set of complex numbers, then you have more flexibility as the value of x which you can use. As to the range or the image set, to the range of f, here we haven't put it with the other characteristics of f, y, because in fact you can calculate it. You can calculate it from the rule f of x and from the domain of the function. Now, the problem now, talking about a function like this, is so general. In other words, a function like this can assume a relation between lines, between planes, between words, between even persons. So actually, this is so general. So we have to define ourselves more strictly. We have to be more precise. So we're going to restrict ourselves only to the kind of function that we are allowed to study in this course. The kind of function that we are allowed to study are real functions of a real variable. In other words, x is real, and the codomain is also R. So now we come to the meaning of a real function. This is the one that we are concerned with. A real function f is a rule of correspondence which assigns to every element x of a subset D of R, this is the domain, a unique element in R. And now we come to the precise definition of a real function. So here D is called the domain of f, and while the set of all f of x for x element of D of f, we call this range or the image set R of f, and it's a subset of R. Of course, these symbols, you can change them. For example, for example, in some books, it can be written D and then subscript F, etc. It's not important, but the idea is the same. So now we come back to the function that we have. They possess some problems. For example, y is equal to 1 over x now. Now, if we have to restrict ourselves to the definition of function, now has to exist. and therefore, and has to be unique. So in fact, this is a function, yes, except that x cannot be equal to 0. So what we say that the domain of this function is R, the set R, with the exception of x equal to 0. For the other one, if you have, for example, this one, y is equal to square root of 1 plus x, same thing. You are only allowed to take x greater or equal to minus 1, because otherwise it's become a negative, and you cannot calculate the square root of a negative number, of course, in our course, and therefore we are concerned with all values of x that are greater or equal to minus 1. And with this, we say that the domain of the function is the closed interval from minus 1 to infinity. Of course, for these two situations, you can also obtain the range or the image set. For example, for the other one, we see directly that you cannot take y equal to 0. And here, for example, you can just directly, actually from the graph, it just says that x varies from minus 1 to infinity, and y varies from 0 up till infinity. And this is the range of the function. Again, when you have something like y is equal to x squared, here you realize directly something which is very clear, that the range of the function is a subset of R. And we call this function an into function. In other words, your range or your image set takes only a portion of R, and it doesn't take all of R. Whereas, for example, y is equal to x cubed, it maps R onto R. In other words, x could be any number for x cubed, and the same thing, the range varies from minus infinity to infinity. But what's important about y is equal to x squared, people sometimes write y is equal to x squared, or x equal to y squared, or alpha is equal to beta squared. You have to remember something. You have to remember that what's the operation here? The operation is square. So actually, when we say function, even the word itself as it stands for what? The meaning, the English meaning, a function, means an operation. So what do you do here? You square this value x. In other words, you use your calculator and you press the button, for example, 3, and then you press x squared to obtain 9. So you do an operation, you do a function. So irrespective of what value of x, whether you write y is equal to x squared, or x is equal to y squared, or alpha is equal to beta squared, or x is equal to y squared, all these kind of things relates actually to one function. It's not that y is equal to a square, meaning that x is equal to square root of plus or minus y. No, it just means that the variables have no meaning, in fact. They only play a role in the operation itself. What is important? What have you done? In fact, you have squared here, and you have squared here, and you have squared here. So actually the function is a quadratic function. This is the operation you are concerned with. And this is why usually mathematicians, in fact, like to represent functions as machines. Machine which accept a value x, and which renders or give it as output the value of f of x. In other words, they differentiate between f and f of x. For example, x could be a fruit, and f a juice extractor, and you get here, for example, a juice. Or for example, you have fibers, and you have a textile machine. So you have textile, garment, for example, here, or you have a textile coming out here. So actually there is difference, in fact, between f and f of x. F is the operation, whereas f of x is the output of the operation. And this is why in some books or in some exam, they ask the student, for example, they tell him, if f is such that f of x is equal to, they differentiate very well between f and f of x. Of course, for a student, you can very well write if the function f of x is equal to, but usually one has to be more precise. But in fact, the result is the same. F is the machine, and f of x is the output of the machine. This f could be represented by arrows. Here, number of arrows are finite. For example, we can assume that x is represents students, for example, in a school, and y represents, for example, fathers of these students in the school. So actually, these students belong to a larger set A, and these fathers belong to a larger set B. And you will find that the function f, what does it do? It maps every student in the school to a father in the set B. And as you realize here, it is allowed that, for example, two students have the same father, twins or even brothers. This is allowed. But what is not allowed, that one student have two fathers. This is not allowed. And this is why when we speak about functions, we have to make sure that every x in A is mapped onto a unique value y. If the number of arrows is unlimited, then you may encounter, for example, a domain of a function as a set. For example, like this one here, a function x which maps x onto square root of 1 minus x. Here, what we do, how would you calculate the domain of this function? It's simple. All you have to do is that you take what is inside the square root to be greater or equal to 0. In other words, 1 minus x should be greater or equal to 0. Otherwise, the square root, we are searching the square root of something negative, of a negative number. So 1 minus x greater or equal to 0 leads to x as less or equal to 1. So in fact, what you have reached here is that the domain of this function is the closed interval minus infinity up till 1 closed from 1. As to the range of this function, it is from 0 to infinity. Of course, you are allowed to use the domain of the function, not the whole values of x permissible. In other words, if you have, for example, something like square root of 1 minus x, you may very well here is 1, because what you put this greater or equal to 0 to give x is less than or equal to 1. So all this is the domain from minus infinity up till 1. But you may very well choose your function in this period only. You may say that y is equal to square root of 1 minus x, given x in the closed interval, for example, from minus 1 to 0. You are allowed to do that. But if you don't do that, then it means that you are concerned with the proper domain of the function. In other words, all those values of x in which you can replace or substitute in the rule of the function. Now, since you have had explained before the concept of a Cartesian product, now we come to a representation like this. Now, it's simple. This representation tells you that the domain of the function is a subset of the values that are taken from a bigger set A, that could be R, for example, and the range as well, R of f. This is the domain D of f, and this is the range, is also a subset of a larger codomain or a larger set B. So in other words, what you really have done is that you said that your ordered pair AB, where B is equal to f of A, in fact stands for one graph that pertains or that belongs to the Cartesian product D of f cross R of f. But in fact, this Cartesian product can allow for many functions. Suppose, for example, that you allow something like this. You say, for example, that the area of a sphere is equal to 4 pi r square, where r is the radius of the sphere, or that the volume is equal to 4 over 3 pi r cube. In fact, these two functions are different functions, of course, in terms of units, but at the same time they have different relations. But look at R. R varies from 0 to infinity, and the range of S, or either S or V, also ranges from 0 to infinity. So these two functions, as a matter of fact, have same domain and same range, but they stand here as different. Here, this is, for example, one graph. You may find another graph also, and we spoke about this when you spoke about real numbers. You said you choose one relation X, R, Y, such that this relation is only partial subset of the Cartesian product D of f cross R of f, and each one of them stands for one special function which you choose, or which you set up yourself to discuss or to study. For example, here, determine the domain and range of f if y is equal to modulus x. This is simple. This is the absolute value of a number. It's clear that any value, real value that you put here, your calculator will calculate it, and therefore the domain is R, and the range, since the absolute value is positive, then the range stands from 0 till infinity. Of course, it starts from 0, y, because when x is 0, y is 0. So if it is positive and there is a value at which y is 0, therefore the range or the image set of this function starts from 0 up till infinity, and the domain is R. Again, suppose, for example, you have a function of this sort. Now, it's 2x plus 4 when x less than 0. And it's x cubed when x is bigger or equal to 0 and less than 2. And again, it is 1 when x is bigger than equal to 2. How can we study this function? It's a rule, but it has so many rules. It has a rule for x less than 0. And it has, if you want to draw this function, it's easy. What we can do, it's equal to 2x plus 4. So 2x plus 4 is something like this. At x equals 0, it's not defined for 0. And then you have x cubed here. When 2 gives 8, and this is 4, and this is 0, and this is 2. So at 2 also is not defined at 2. And then it is equal to 1 like this. This function, as a matter of fact, when you see this function, it stops here at 4. So actually this rule is not defined for 4. But the region here, the values of x one can use are all those values of x belongs to R. Because in fact there is no such x which you cannot substitute for in the rule of these three rules. Or in these three rules, there is no such any x which you choose belongs to one of these three intervals in which the three rules are defined. But what about the range of f? You find very well that there is a ceiling 8. What is the value of 8? 8 is the least upper bound. There is no maximum. Why there is no maximum? Because 8 does not belong to the image set of f. So actually this is the least upper bound, and it's easy here. This function has no maximum. Here it is. Here it is. Here the domain of f is R, because f is defined for all values of x, whereas the range starts from minus infinity, because you have here 2x plus 4 is defined for all values of x less than 0. And then it goes up till 8, here the value 8. And there, it doesn't go beyond the value of 8. So 8 is the maximum, not the maximum, but the least upper bound. This function has no maximum, least upper bound of this function. Now suppose you have a function like this. The domain and range of f, given f of x equal to x minus 1 divided by x plus 1. You have to, for the student, you have to know how to draw graphs of this sort. Like, for example, x plus 1 divided by x minus 1. Or even x minus 2 divided by x plus 3, etc. All these kind of functions. You have to know how to draw it. For example, for the first one, you do it simply. You choose any points. For example, if you take x equals 0, it must pass by the value x is equal to minus 1. Again, when x becomes very large, either positive or negative, this tends to 1, because 1 million plus 1 divided by 1 million minus 1 is almost 1. So you have what we call an horizontal asymptote of 1. Also, when x is equal to 1, it's not permitted. So here you have a vertical asymptote at x is equal to 1. So how can how can we now draw this function? It's very simple. It must be like this. It passes by this point. And here, when x is equal to minus 1, y is equal to 0. So it must pass also by this point. So you have something like this. What about the other one? The other one is like this. It has a vertical asymptote at x is equal to minus 3. It's not defined for x equal to minus 3. This function here, the domain is what? The domain is R, with the exception of what? Of the value x is equal to 1. Whereas here is R, with the exception of what? X is equal to minus 3. So at minus 3 here, at x equals 0, so it passes by this point. And then same thing, you have here 1, and there is a root at 2, so it must be like this. There is no other way of drawing it, etc. I mean, all these kind of functions, 2x plus 3 divided by x plus 5, etc., etc. All these kind of functions, one has to know how to draw it, because they're simple functions. So for this particular function here, it's simple that you can substitute, you can use the meaning of the domain of the function. It means that all those values of x which you can use, can replace here. What value of x you can use? You can use everything, and you check with your calculator. Every value of x is admitted, is permitted, with the exception of x is equal to minus 1. So we say x is equal to minus 1 does not belong to the domain of the function. Therefore, d of f is equal to R, with the exception of x is equal to minus 1. Now, what about the range of the function? Of course, from your drawing, it simply appears that y is equal to 1 is not accept it as well. In other words, there is no such x corresponding to y is equal to 1. But you can do it in a different way. What you can do is that you can write x is equal, y is equal to x minus 1 over x plus 1. That's our relation. And then from which you can extract x in terms of y. In English, we call this in mathematics x subject. In other words, you solve this equation, which is very easy to do it. Yx plus y is equal to x minus 1. And then you get x on the left and y on the right to obtain a relation of this sort. It does seem very clear now that y is not permitted to be equal to 1. There is no such x corresponding to y is equal to 1. Therefore, the range of the function is what? Is r with the exception of r equal to 1. And then you write down your function. Whether you write it this way, there are different ways actually of writing functions. You can write it this way. You can write it as the set of order pairs, x, y, such that y is equal to x minus 1 divided by x plus 1. Or what you can do is that you write f, which brings every x into x minus 1 divided x plus 1. Of course, you may write x is equal to minus 1, but you may not do so as well because it's understood inherently, implicitly, that it's not permitted to use x is equal to minus 1. Now, obtain the domain and range of function like this one. It's easy. Now, without drawing even, some students usually ask the question, should we always graph the function? Because they find difficulty in graphing function, and this is why they might use calculators. But you don't have to. It's easy. Here you have square root of 2 minus square root of x. Suppose we want to discuss or to study this function. It's simple. Since you have here square root, we said before, x should be greater or equal to 0. But again, what is inside the larger square root must be also greater or equal to 0. So with these two inequalities, you get the domain of the function from 0, the closed interval from 0 to 4. Now suppose this is the domain. This is usually the easiest part of the question, of the problem. Usually, what about the range now? Is it difficult? Should we get x in terms of y? No, you don't have to. Why? Because directly, since this is the square root, so it's positive. Meaning that the range always stands for those values of y which are positive. Now the problem is that, do they start at a point and end at another point? Yes. Why? Because from here, you directly notice that every y is less than square root of 2, because you always subtract from 2 something here. So it must be less than or equal to square root of 2. So this is the maximum here. And at the same time, does it exist a point at which y is equal to 0? Yes. If you put x is equal to 4, you directly get y equal to 0. So in other words, it's simply your problem tells you that the range of the function varies from the closed interval from 0 till square root of 2. So in fact, you don't have to always to check with the drawing or manipulating in order to sketch your function. All you have to do is that from what you decide to do to study the function without graphing the function. Suppose we want to study something like this: x squared minus 5x divided by 5x minus x, x plus 1. It looks complicated, and this is the graph of the function. Without the graph, it tells you directly. Since this is square root here, you have to have this bigger than 0. But again, modulus x plus 1 is always positive, so you don't have to take this into account. So you have x minus 3 times x minus 2 divided by 5 minus x. So directly what to do here, you have 3 sets like this, 3 lines. You have x minus 2, you have 2, and you have 3, and you have 5. So this is positive, and this is negative, again positive, negative, again positive, negative. Now what you require is what? What you require is that since you are here, you're taking x minus 5, then you must revert this sign here. So you need to the intervals at which f is negative. So from 3 to 5, it's negative, and again from what? From minus infinity till 2. So you have either this interval or this interval. And you don't forget to divide by 5 here, and therefore you have to exclude 5. And in fact, you exclude 5 and minus 1 also. Why? Because at minus 1, the function here goes to infinity. It has a vertical asymptote. And at the same time here, as well as x approaches 5 from the left, this goes to infinity. Of course, from 2 to 3, what's inside the square root is negative. So the function does not exist. You cannot replace x by value between 2 and 3. And at the same time, for x bigger than 5, you cannot also choose x equal to 6 because it doesn't work here. So actually, of course, you can, as I said, you can draw your function. You can take points. This is usually what the students do. You don't need really calculators, but drawing graphs of functions, it tells you directly the values of x which you can only use, are permitted to be used. But as we said here, as we discussed this problem, all you have to do is that to take lines and you consider when you have directly when you have square roots, then it means that what's inside the square root is positive. This gives you the domain of the function. And since you have a square root, then the range also is a set, the elements of which are all positive also. There remains only one point. What are the values of y? So you can actually either take points or you take the limit values such that for y, for example, if there exists a point at which y is 0, so it starts from 0. Does y goes to infinity, etc. And this actually gives you directly the domain and range of the function. Here is a problem in which you don't need to draw your graph at all. You have a square root, so what inside the square root must be positive. But if you write the square root in this form, it simply tells you something directly, that your square root must be less than, more than square root of 11 over 3, because this is positive. So you add up a positive number to 11 over 12 square root, it must be bigger than, larger, greater than square root of 11 over 12. It also tells you something else, that the minimum is attained at x is equal to 1 over 6, because any value of x apart from 1 over 6, whether less or greater, makes you this positive and greater than the square root of 11 over 12. So in fact, any value of x is permitted, and therefore the domain is R, whereas the range of f starts only from the square root of 11 over 12. And this you don't need actually to draw such a graph. Finally, when you have functions, if you add up functions or you subtract functions or you multiply or you divide, it's simple. You add up exactly like numbers. For example, x squared plus x cubed. Can you add up these two functions? Yes. X squared plus x cubed. It's a function. But the problem is that what is the domain of this function? It directly tells you that the domain of the addition or the product or the difference or the division, the quotient of two functions, is the intersection of both domains. Of course, here you have to exclude the values of x at which g of x is equal to 0. So for instance, if you have square root of x is equal to 9 minus x squared, and g of x is equal to x squared minus 4. Here directly we have the addition f plus j is equal to, you add up these two, and of course here this is defined over R, whereas this 9 minus x squared must be positive. In other words, x lies between the closed interval minus 3 to 3. So when you add them up together, you have to also get the intersection of these two functions. In other words, this function, which is the addition of the two, only works in the range from minus 3 to 3. And this applies to fj and f minus j and f over j, etc. And here it's an important thing to say that even if you have f squared, what you do is that you remove the square root. Even here, if it looks as if it is R, the domain of this function is R, but as a matter of fact, it works from minus 3 to 3. Why is it so? Because in fact, what you do is that you calculate the square root and then you square the square root. So since you calculate the square root, then it might function only between minus 3 and 3. And then it's immaterial whether you take the square or not, but in fact, it is between minus 3 and 3. In fact, if you want to consider, suppose you have a complicated function of this sort. For example, x minus 1 times x plus 2 divided by x plus 2. For example, x minus 3, you have something like this. Or for example, let's take x minus 5 times x plus 3 divided by, suppose again x plus 3 multiplied by x minus 3. Suppose one gives you a function like this and asks you to study it. Directly you say, here you have to cancel this out. But if you cancel this out, here this is f and this is j, and the domain of these two functions is the intersection. So directly the domain is what you have to exclude those values of what? Of minus 2 and of 3. Again, you have here minus 3, and you have 3 again, so it's finished. Now, suppose you want to give the range of this function. What you do is that since this is exempted, these values are exempted from the rule of the function, so you might as well do this. And you end up with what? With x minus 3, and you have here 4, 5, yes. And so how do you suggest this graph would look like? This like this, and then this is the horizontal asymptote, because at x tends to infinity this gives 0, and then at x equals 0 it is negative, so it must look like something like this. It must look like this. But again, there is a problem here, because you have to at the values of minus 2 and 3 and minus 3, you have here minus 2 and here minus 3. You have also to what? To calculate those values of y in which x is equal to what? Minus 2 and minus 3. So if you put here is equal to minus 2, you exempt from the range of f minus 4 over 5. And you also exempt what? Minus 3, minus 4 over 6, minus 2 over 3. In other words, there are two values of y which are, in fact, there are three values. Y is equal to 0. This is one value exempted from the range of f. There is also the value at which x is equal to minus 2 here, which is minus 4 over 5, and minus 3 as well, which is minus 2 over 3, are exempted from the range of f. So the range of f is what? R, with the exemption of the range of f, R with the exemption of what? Of 0, and minus 4 over 5, and minus what? 2 over 3. Those are exempted from the range of f, because you have 2, it's true, minus 4 over 6 is true. This is how things go, in fact. It's not difficult. Given anything, you just you have to imagine how things go. You manipulate, and then you cancel those values of x which you cannot work out the value of your function, etc. With this, we have come up to the end of this lecture. And we have we have explained what's the meaning of a function. And we said that the function looks like a machine in which it accepts only some values of R only that are permitted. We call them domain of the function. And these values correspond to other values of y, which we call the range of the function. And then we have been able to calculate some domain and range of some functions. And finally, we have spoken about rules, algebraic rules of functions, and how you add up a function or you divide functions, etc., provided that, or if it's in the denominator, it's not equal to 0. And you have to get the intersection of these functions in order to obtain the domain of the addition, or the two functions together, whether they are added together or subtracted, etc. Finally, I wish to remind you that this lecture is uploaded to the site of MedNetU, which is the project administered by the Consortium TUNU of Distance Learning. And you can find all these lectures. Most probably they are going to be put soon. And next time we shall speak about the classification and the properties of functions in general. And until we meet, I thank you very much.